BZU webinar series, proudly presented by IEEE Ziauddin University Student Branch in collaboration with BASME BME. This is session 5 of our ongoing series where we explore not just academic excellence but also the personal journeys that take students and alumni from the classroom to the world of groundbreaking innovation and discovery. Today's session is a truly special one. We're taking you on a journey from molecules to materials to the eyes of someone who once walked the same hall as many of you. Whether you're still in your early semesters or planning for grad school, this session will help you envision how a degree in health or engineering can evolve into something global, interdisciplinary, and truly impactful. Our guest speaker for today is Mr. Ahmed Shaukat, a postdoctoral research associate at Durham University in the UK and a proud alumnus of Ziauddin University. Mr. Ahmed began his academic career with a PharmD from Ziauddin and later pursued a master's in biosystems and biomaterials engineering, followed by a PhD in bio-nanotechnology, a field that merges biology, nanoscience, and material engineering in some of the most exciting ways. Mr. Ahmed now works on cutting-edge research in DNA origami and protein cages, showing how curiosity and courage can shape powerful career shifts and global impact. Please join me in welcoming Mr. Ahmed Shaukat. Sir, over to you.
Okay, thank you so much for the nice introduction. I think I will now share my screen. Right. Can you see the screen now?
Yes, we can.
The whole PowerPoint, like the presenter view, or the presentation itself, right? Full screen.
Yeah, we can see the full screen.
Right. Thank you so much. Yeah. So, what I would do here is I would tell you what I did, from Ziauddin to Durham itself, the whole journey, and then what are my, let's say, the reflection of what I did before, and then what I'm doing now. So there would be some science as well, but most of it would be the journey itself, right? The takeaways from what I did during that time. So what I would start with is right. So I completed my PharmD in 2013. There I am, not thinking about the future. That basically is right after this. It was a really good time. I think there was only one campus. Let's say in Clifton, there were two let's say two different campuses right in front of each other. There was College of Pharmacy, like 3 floors of a building there, and then the hospital across the road. So we were distributed between the two, let's say, buildings there. Really good memories there. Then what I did was 1 year on-job training in AKU as a pharmacist. This was basically what it gave me is that it gave me let's say some insights that how a tertiary care hospital works. There was like clinical pharmacy, inpatient pharmacy, outpatient pharmacy. So we were basically stationed in all these pharmacies one by one, and what the idea was to get taste of every other like sub departments and then see where you fit the best. And by the end of it, you would give they would give you, let's say, an opportunity to join one of the department for, let's say, as a permanent position. So unfortunately, I did not continue this. I think by the end of it, I knew that this is not something I want to do for the future. So I then decided, okay, so at that point, I think I was still looking to go abroad for my master's. Unfortunately, I didn't have the, let's say, the means at that point. So I was still looking for ways to go for my master's outside. Then came the corporate job in 2015 in Sanofi. This is the building. I think now this has been uh, changed to.
Excuse me. I'm sorry to cut you off. I just want to say, can you open your presentation view? Like we can see the whole PowerPoint, but not the presentation view.
Right. That's what I was asking. Yeah, that can you see it? Right. Okay. Let me go back.
Yeah, now we can see it, but it's still not the presentation view.
Right. Right. Can you see it now?
Yes, we can.
Okay, I can go back again. So, right. So I completed my master's. Again, some pictures so that you can relate what I was saying before. So there I am at the bottom, here, and then started my on-job training, like pharmacist training in 2014. I think there were around 20 people in one cohort. So they were getting 20 people every year, and then most of them, let's say, continued, or let's say half of them continued in the AQ, and then half of them left. Some of them came back to do again this job. I unfortunately did not see myself as a hospital pharmacist, so I discontinued, and I think I never looked back. I think I don't remember exactly now what I did in my pharmacy because that was 10 years ago. I still remember the foundations, yes, but like the names itself of all the drugs that I learned at that point, I don't remember it now. Right. Then I went to, let's say, get a taste of a corporate world. That was Sanofi back in 2015. I think I did 2.5 years there. It was mostly a corporate job. Let's say it wasn't that great in terms of, let's say, learning something new every day, and that's why I was like, maybe it's not something for me as well. I still wanted to do a master's, a very research oriented master's, and that's where I think I got an opportunity to, let's say, move abroad to Finland, where I did my master's. This is the campus. It gets really cold, like in -20 in winters. uh, I started in 2017, did my master's until 2019, and then I started my DSc, so Doctors of Science, and then I defended that in 2023. This was the so this was my supervisor Mauri Kostinen. He's holding this cap, so you basically get this cap when you pass. This cost a lot, so I didn't buy it. Basically, it's really costly. Yeah. And this was my opponent, Tobias Beck. This was he was coming from a German university, so I had to defend what I have done. Let's say research of 3.5 years. So what I have done, why I have done this, and then let's say he wanted to test me whether I've done all the experiment by myself or not. So this was done right in 2013 October. And from then on, I went to, let's say, to the current my current university, that is Durham University. Right. Okay. So I started in 2013 or 2023. This is technically not the campus itself. The campus is somewhere here. This is the cathedral, which I think when you search Durham University, it will give you this picture. But this is the cathedral. You get your convocation here for the university. It's a really good city. It's very, I would say, small, but still very peaceful. And this is the entire group. There I am, standing at the back. This is the professor I work for, Jonathan Heddle. And this is the whole group. So it's a really big group. We have I have one PhD student right there. It's a very diverse group in terms of we have a chemist, we have physicist, we have a structural biologist. Me working as a, let's say, primarily I would still call myself as a pharmacist because I was trained as a pharmacist. but then I went on to, let's say, to do different degrees in engineering, let's say biomaterial engineering, and um, uh, the PhD in Bionanotech. So I would still call myself as a pharmacist because I was trained as one. And the center that I work for is Center for Programmable Biological Matter. We basically do artificial proteins at the moment, DNA origami. I would tell you some things, like I would tell you some science, let's say what we do in the center, as well as what I did in my PhD as well. Uh, so as a center, what we work is making artificial cages, DNA origami, and then some DNA gyres as well. So one of the enzyme that is basically responsible for, let's say, microbial resistance. So we also work on that as well. So if you are really interested, you can search for this center uh, or the Hedel group in Durham. Right. So this presentation would be about the journey. So I would start with what I did at Ziauddin. So the first thing that came to my mind was it had excellent teachers. Um, I can still remember those, let's say, few teachers that were really good in what they taught. The organic chemistry, the pharmaceutical chemistry, that I still have, let's say, some great foundations from there. Um, so I would say that I still believe that they still have the, let's say, the quality teachers they used to have now. I was looking very recently at the website, and then I think some of them are still there. So it's really great to, let's say, see them there doing the same, let's say, teaching. Uh, then what I would say at Ziauddin, I think it laid a really good foundations for hospital or clinical pharmacy. So if there are students from pharmaceutical background or pharmacy background, I would say comparing what I had, let's say, comparing to the other colleges that the people that I met during my, let's say, time at AKU, I think I can proudly say that yes, we had really good hospital and clinical pharmacy foundations. Um, and as well as pharmaceutical chemistry or pharmaceutical sciences. So, but I think the overall PharmD curriculum, I think it was primarily focused on having really good foundations for, or let's say, having good background for hospital and clinical pharmacy. Right. One thing I also remember is having lots of cats. I think the abbreviation was continuous assessment test, if I remember correctly. Uh, it used to keep us on toes. So I think it was maybe 10 weeks, or I don't remember exactly, like 15 or 10 weeks after the semester starts, and they were two, I guess, at that point. So we were revising everything that we had done 10 weeks before. So I think it kept us on toes. If I can reflect back, I think it was really good. By that time, I was cursing it that it's not great to have, let's say, too many assessment tests right after each other. So, but then when I look back, I think I can say that this was really good. Right. So time at Ziauddin was really good. Then came time at AKU. So I again, it's really ideal for practicing hospital as well as clinical pharmacy. Uh, it had lots of, let's say, sub pharmacy, like Ibn Zohar, or uh, talking about outpatient pharmacy, so CC pharmacies or CHC pharmacies. So these were all different flavors of what you can get in inpatient, outpatient pharmacy. In inpatient pharmacy, I used to work in ICU as well as CCU, or those wards that are inside the hospital. So you get flavor of every pharmacy inside this tertiary care hospital. So the time was really good. But one thing that I was really like, I still remember, it was really tough for interns explicitly. We used to walk the whole hospital, like we had to travel from one pharmacy, especially interns, because those were the workhorses of the pharmacy itself. So there wasn't any trolley or any auto automated delivery for us. So the interns used to travel from one pharmacy to the other, just to, let's say, so if one pharmacy was short of one drug, we used to travel from one pharmacy to the other. So it would, and this is a really big hospital, so that was really tiring and really physical exercise that we used to do every day as an interns. And sometimes we used to also dispense at the back, work as a technician, and then we used to dispense all the medicines. You have to be really fast, because there's lots of line, let's say, to cater, or let's say address, when a pharmacist is basically dispensing in the outpatient. So the outpatient itself was a bit tiring, and then very happening, I would say. Yeah. So uh, right, time at Sanofi, it was again like a corporate job that was in commercial quality or affiliate quality. Again, doing nothing but, let's say, doing some paperwork or reading. But I think when I reflect back on that time, I think even small things that I think made a really big difference, such as like small things like writing a good email, like getting work out of someone very politely, or like even like talking like professionally. By then, I don't think so I was that professional, but then Sanofi, in a way, that molded me as a working professional doing a corporate job. So that I think I can still take something away from that period as well. Um, right. The work itself was basically doing quality operations. So I was responsible for keeping medical, clinical, or regulatory, or supply chain, or even the information system. So the IIS systems, let's say, operations as per company standards. So it's basically similar to what audit, let's say, finance audit person would do to finance department. But in my case, I was doing it with medical, clinical, or regulatory operations, so that they are working according to, let's say, company standards. In this case, Sanofi had a really high standard, as an international standard, for keeping everything in place. So keeping patient compliance, or let's say that doesn't hamper, let's say, patient the patient information is not going outside the company, or we are keeping the supply chain consistent as when the drugs are reaching the market. So everything under that was basically my responsibility. As per every other pharmaceutical company, they had really good food. The canteen there was really good. The thing that I remember most is still the food that got served in the canteen. So that's something that I still remember. Right. So then when I went, so from there, I think I started my master's, right? So I started in 2017 autumn. This was basically a master's in science, technology, in biosystems and biomaterial engineering in Finland. So what I would say about Finland as a country is it was technologically very advanced. I still don't remember going to any government offices for getting anything done. It was all online. Even the transportation system was really good, and technologically advanced. I think it's and comparing to other European countries, I think Finland did stand out as other Nordic countries would be. It was a very introvert friendly country. I would say that, because me being a very introvert uh, personality as well. So people would keep distance with you, I guess. It's at some point, I mean, at the start, you would feel a bit awkward that why people are standing away from you, but it is the norm that they would give you a privacy really good. They won't, let's say, budge, or let's say, even if it's raining really heavily, they would still stand outside like 2 meters away from you. So maybe one of the reason Corona did not, let's say, damage that well was is that they were keeping distance even before Corona. So I guess that's what I like, that they give you really good privacy as well as let's say space in terms of let's say living there. Winters and finish can be challenging there. So winters are really harsh. It's very dark. It gets dark at 1 or 2 p.m., like pitch dark, because it's very north up there. Winters can be challenging, and especially when it's too cold. So it's -20 or -10 when it's peak winters, and the language itself. So I think 90% of the population speak English, but I think they start the conversation with Finnish. I think I've read somewhere that it's one of the toughest language to learn, but I think you can get away with English most of the time. So everybody speaks English there. I didn't had any problems, but let's say the jobs that require speaking to, let's say, the public itself, I think that's where it gets tough. You probably have to learn a language there, at least like Finnish or Swedish. Both languages are common there, so you can get away with Swedish as well there. It's slightly easier, I would say, but still pretty different from English as well as Urdu. So I would say that was a big challenge. People are great as well, so they say what they mean. Um, and they are really straightforward, and they won't speak until, let's say, they mean something or they want to say something, and that's something not common in terms of I would say when people start speaking, so they really mean something, right? So they won't say anything out to please anyone, I guess. That's, I would say, very simply. So well, I finished my master's there. This basically was writing a thesis. And the best thing about that was I was paid to do a master thesis there. That was a really good thing, that I was paid to do the research in one of the lab. Uh, and I had to defend this this thesis as well, not in front of the public, as I did when I did my uh, uh, Doctors of Science, but it was in front of the department itself. And then it was basically explaining what I did and why did I do this. And yeah, so this was, and I did the masters as well as the Doctors of Science in the same group. So I continued what I started doing in my master thesis, and I continued that work into my doctoral studies as well. Right, I cannot recommend enough Alto as well as Finland. Both the university itself, the country, I think it's a really good university. When I was starting my masters, this was recommended by an HHS student. He was basically, I would say, a friend as well as a person living nearby my house, so a neighbor precisely. So he met like out of nowhere and then said, yeah, why not, why don't you? So while I was in Sanofi, I basically met him, and then he said that, why don't you try coming to Finland? It's a really good university as well as a country. So the winters are, he basically was joking that the winters are not that great. It would be really hot there. But I think now I think that he was joking. Um, right. So he said that he should try to, let's say, come to Finland as well as Aalto. He was still studying there, and I think that was one of the best decisions that I made in my life, coming to Finland as well as doing a master's and PhD there. So I cannot still like recommend enough going there. By the time that the time I went there, there wasn't any tuition fees. Unfortunately, due to external, or I don't know, internal pressure, Finland started putting tuition fees for international students, but they do offer scholarships that are basically, they waive off your tuition fees entirely. the only drawback, or let's say the condition, is that you need to complete the masters in 2 years, which mostly people do. um, they probably might give you, let's say, a 6 month extension based on if you're doing your master thesis. But mostly people do complete it in 2 years. If you get a scholarship, I think that could be the best thing that you could do, doing a master's in Aalto explicitly. But Finland itself, the other universities in other cities are as good as Aalto. But what you can do still is that if you get an admission in Aalto, you can take courses even in other cities and other universities as well. So there's no blockade, or let's say that if you have admission there, you cannot take courses there. If you find a course in any other universities, you can go there and do that course by yourself. Nobody's stopping you there. So that's also really good about the education system, that if you find a good course, a good teacher that is basically in other city, you can go there and then do that course as well. Right, enough of let's say me telling about Aalto and Finland. So yeah, this is the thesis that I did in Bionanotechnology in Alto. So I think I would tell you something about in the next few slides what I did there, but it's basically making structures, high order structures using electrostatic forces. So there will be some background of what I did as well, but this is a book style article based. So I had to publish 3 articles before I published. Um, and to give you a
Mr. Ahmed, we have some questions, and you can take questions during your session. Okay, you can ask the students to ask some questions, and I can tell you the questions that are in the chat box if it's okay with you.
Uh, I can stop now, and then if somebody can tell me the questions, that would be great.
Okay, so I have a question from Shezil Kashif, and she's asking that do you think Pakistan is moving towards research in areas like bio-nanotech?
Oh, I unfortunately do not know what's happening in Pakistan at the moment. I think, well, looking at like how AI is getting into everything, uh, I would say it's not that far that people would start looking into, let's say, if people know how protein folding works there, right? So alpha fold 3, and then those are available to every individual. I think it's not that far that at least people can do in situ, or let's say computational like computer simulations studies there. So it would be difficult to do, let's say wet chemistry experiments there because of the financial constraints. But I think it it's not that far that people in Pakistan would start doing this kind of work.
Okay, cool. We have some more questions. If you want to, I can carry on.
Yeah, sure.
Okay, we have one more. How different is the research culture abroad compared to Pakistan?
Uh, right. So I did one research article in Pakistan back when I was doing my pharmacy in Ziauddin. Um, I would say, based on uh, the instrumentation available, it's it's a bit hard to do experiments, the same experiment that I would do here in UK or in Finland. I could not do that there, right? So such as, let's say high tech microscopy, like TEM or SEM. I don't think so that was available in Ziauddin by the time I was there. It might be available in Karachi University. It might be available in NUST, or let's say somewhere in really like other universities. But you probably have to have really good collaborations Here it's slightly more available. So it's it's a bit challenging to do the same experiment there, and I think it's very like uh, I would say very easy to say that it cannot happen. But due to financial constraints, again, I would say it would be a bit different, right? The culture itself, I would say, again, it's a bit different. The way people do research in Pakistan, I think there are lots of people involved in just one small experiment. But here, it's probably you are only the one that are you're responsible for your own experiment or your project. And then you would be designing your own experiments and then working along. So I guess it's a bit different in terms of how people work. Again,
Yeah, you like get a bit more free hand
I
abroad
hope.
rather than in Pakistan. Yeah, we do get your point. That was amazing. We have one more. We have a few more questions. If someone is interested in research but comes from a non-research university, what can they do?
Right. I would. So that's what I would do at least. So usually, what you need to do. So if you can't do wet chemistry or let's say experiments in a lab, I would start researching, let's say, or like even maybe writing a review article based on the information that I can get from internet, right? You can still write a good review article, and then publish that. So that basically gives you an idea, or it's an edge, that you know the background, right? Even if you haven't done any experiment, that's what I would do, and I think I did that as well, to just, let's say, just get the in and out of a field. So for me, being a pharmacist, DNA origami was a completely different world, right? So I basically did a small review just to, let's say, get to know how that, okay, what how does this happen, why does it happen. um in pharmacy, I didn't had any like not strong background of biochemistry or physics, or let's say, so I had to, let's say, work a bit more than the other students just to get what they are getting as well, right? So I would say, if you want to do interdisciplinary research or any research that are out of your comfort zone, I would start researching. And maybe, so once you are writing or let's say researching it, it's a really good idea to even publish what you have written. So I would probably start writing a review. That's what I would do at least.
Okay, that was a very great explanation. We have tons of questions coming along, so we can first continue with your presentation and then do a Q&A session at the end. Is it okay?
Right. Yeah, sure. So, right, going back to the journey itself, right? So this is the thesis that I did. Again, so this is where I did my defense. It was a really formal kind of a setting, where he had, I guess, 2 hours to ask any questions out of my thesis. So anything he found, let's say, questionable, he would ask me there. So I was responsible for explaining line by line why I have written this. So it was 2 hours of really, like, I would say, intense discussion. But I think, looking back, I enjoyed that. I was really nervous as well. And the story behind this crystal is that we basically tried to make a crystals out of those some so proteins that I basically work with. And what we did was, basically use FRAP technology, so fluorescence bleaching. So we basically bleach this area using high, like a laser beam, and we this is the logo of the Aalto University, and it's basically on top of the of a crystals, and that was basically the cover page of my thesis as well. So this is something that I thought, let's do this while I was imaging these small crystals as well. So uh, again, something I still remember, yeah, and enjoy doing this as well. So I thought let's give you some reason behind as well as the science behind this thesis. But before that, I think I probably have to give some background, right? So I used to travel in this particular bus. So I used to take this bus, explicitly this Khan coach from Hedri, let's say, to Ziauddin, to Clifton branch. And this is how I used to find it every day. And I used to, let's say, stand there in like here with one of my leg hanging around, and some of my like friends were on top of it as well. So just to give you a background, right? So think of this as a material, right? This material looks like there's no port, right? You can't go in. There's no symmetry. People are like standing um, randomly here, and there are no pores, right? This is aggregation, right? So the aggregation can lead to loss of biological activity. So if it was a material that was, let's say, that had a function, I think aggregation can lead to, let's say, loss of biological activity, right? And there's limited accessibility to go inside the structure. Like this bus, you can't go inside very easily. um, so again, having a structure with no orientation or, let's say, symmetry can have limited accessibility, right? And it is very hard to predict the structure itself, right? So think of this as a material, right? And then I give you an example of a finished bus. This is how exactly I found them as well. So if you look them, they are sitting like one seat is empty and the other person is standing right there. So what you see, think of this as a material, right? There's high order of symmetry, like people are standing, like sitting right to the window itself. Nobody's sitting on the other window as well. So there's symmetry there, right? This may lead to enhanced activity. So right, again, this is just a comparison, right? Like a material. So and there's high accessibility, so you can sit anywhere you want because this seat is always available. So there's high accessibility, right? The structure prediction is relatively easier, so you can predict that everybody would sit there, so you know where everybody would sit, right? So what we know from this is that the materials with nanomaterials with ordered structures are desirable, right? So this based on the things that I said, that okay, having a robust structure or high order structure, they may lead to a desirable structure. It doesn't mean that amorphous structures or materials do not have functionality or better functionality. It just means that maybe sometimes when we have an ordered structure in materials, we might have, let's say, a better activity or enhanced activity, right? Okay, so right. So how do we assemble nanomaterials in order structures? So just to give you some background, right? This would be some slightly more scientific slides that are coming up. So right, uh, how do we assemble structures? So what we have is building blocks, right? So any molecule that we have can be used as a building block. So proteins, DNA, elements that we have, compounds that we have, can be used as a building block, right? So what we need, they need to self-assemble. So we don't need to put them in chemical synthesis or anything. We don't need to put any force apart from what they have from inside, and they have their own interaction, so intrinsic interaction, and that can lead to ordered or amorphous structures. So that the self-assembly, it's a term that people use in chemistry or physics or even biology, that they self-assemble into ordered structure, right? And this is basically similar to what we have as Lego bricks, right? So we basically make our structures, and we can make different structures out of Lego bricks, right? So what type of interaction we can use? This is sort of some physics and chemistry. So if you remember, we can have metal coordination. So metal ions can be used to, let's say, make a self-assembly. We can use hydrogen bonding. If you know, that can also be used to, let's say, interact. This is the one that I have used. So electrostatic interactions. So we have a positive body as well as a negative body. They interact each other based on the charge they have. and they have pi-pi interactions as well. So we could use basically pi interactions to form different kind of self-assembled materials as well, right? Self-assembly around us. So what we see around, so human body itself has lots of materials that are self-assembled. So proteins, again, self-assemble into the structure that we know of, right? We have food around us that has self-assembled structures. So lipids or anything that you find inside the proteins itself, the carbohydrates, again, have self-assembled structures. The shampoo and the conditions that we use, again, have self-assembled structures. So the lipids, or let's say the emulsifiers, everything that we know, the ingredients of the shampoo and conditions have self-assembled structures in them. The animals that we see around, the color that we see is basically of the self-assembled structures or proteins that results in this kind of a structure. So the things that are responsible for these structure is, again, the biomolecules that we find in our environment or in ourselves: carbohydrates, DNA, lipids, or proteins. The center point of my thesis was basically using protein and DNA. So in DNA, what we find is having base pairs or pi-pi stacking or hydrogen bonding between the base pairs, as well as in proteins, when it folds together, we have hydrophobic interactions as well as hydrogen bonding to have, let's say, the structures of protein as we see them, and that's the structure is responsible for its functions most of the time in terms of protein, right? And the good thing about these two, let's say, biomolecules is that they are intrinsically charged molecules, right? So I can play with these charges to make the structure. So with DNA, we have a phosphate backbone that is negatively charged, as well as the proteins. The proteins that we find usually have some sort of charge in them. So they could be negatively charged or positively charged. So what I did was I played with the positively charged, let's say, amino acids or proteins itself, right? So what I did was use electrostatic self-assembly. So in order to explain how it works is that we have charged bodies. So we have negative and positively charged bodies, right? Um, what happens is that when we mix them together, right? If there's no screening, or they are, let's say, they are charged together, um, what happens is that they bind it together very tightly, and you don't see any structure, right? But if you put too much, like ionic strength, or let's say in this case sodium chloride, right? So that can act as a screening agent. So it basically protects them to bind with each other, right? So if you put lots of sodium chloride in this case, they would not bind to each other because they are basically around those charged bodies. And if it's a negative body, there's sodium ion around this, right? So they won't bind to the positively charged molecule, right? And they won't bind, or they won't have any structure. So if we take away, let's say, or we have a perfect amount of sodium chloride in it, we can have this kind of structures. And this is what I did in my PhD as well. So to create these kind of structures, or let's say using just ionic strength or electrostatic self-assembly. Right. The material that I used was a DNA origami. So we see this. So if you remember, DNA is two strands, like double strand, right? So we used a single strand unit. This is single strand, and we have multiple short staple strands. So they basically use to fold the DNA structures into any shape or form. In this case, it's basically making a 2D rectangle, right? So you have one structure. It's basically similar to what origami does, right? So origami is basically folding the paper into any shape or form. And in this case, what we do is fold the DNA, a long strand, one single strand of DNA into any shape or form. So small staple strand staple the DNA structure itself. And this can be used to, let's say, make any structures or form, right? So this was basically done in 2006 by a Caltech engineer, Paul. So what he did was make different structures out of the same technique that I showed you, origami. So making 2D structures, a smiley face. Um, Again, so this was done. Then basically make world's smallest painting. If you can remember this painting, this was again done by making small tiles of DNA origami and then joining them together. to make this famous painting. This can also be used to make this small robots. So if there was a famous physicist, Richard Feynman. He basically said at one point that there would be small robots that could be delivered to a body and then do different stuff. So we are going into that, let's say, uh, uh, in that way, that we basically make small robots that can swim into your body and then, let's say, kill the cancer cells or deliver the cargo that we wanted the cargo to be delivered to that specific organ. So we are going into that direction. We can also make like a box like structure or a capsule like a structure, so where we have different cargo inside, and then it would only open where we need it to be open, right? So there would be a stimuli that would open this box, and the cargo that is inside would come out, right? And this way you can basically do target delivery or drug delivery systems. And you can also make these kind of capsules that opens and closes based on the stimuli that we provide. So you can deliver antibodies or anti-cancer agents through this. So we know that the anti-cancer agents such as doxorubicin, what it does, that it also, so when we are giving this drug, it basically goes to every part of the body. So it's not just cancer cell, right? It's going to the healthy cells as well, right? And it's killing those cells as well. So what we want is that those drugs can only go to the cancerous organ, right? And that's where these kind of drug delivery systems comes into, let's say, play. And these structure can only open based on the stimuli that we basically put inside, and they would only open when we say, when we say, so based on light, based on let's say sound, let's say based on the nucleotides that are present, or the antigen or protein that is present there, we can open these up. So that's where it's basically going, and it's a really good technique to, let's say, to deliver cargo there. DNA origami, it's not just only for biotech or, let's say, drug delivery. It's being used in material science. It's also used as a programming language as well. So if you're really interested about using DNA as a programming, let's say similar to what let's say the logical sequence 1010, we can use the DNA sequences as those logical sequences as well. So if you're really interested in that, you can check that as well. Um, so yeah. The proteins, again, the similar construction material that I use. This is basically how the protein folds into the quaternary structure, right? So we have primary structure that is transcribed from the DNA or from the RNA, basically, and we have this kind of a structure which is unfolded. That then it converts itself into a secondary structure, then a tertiary structure, and then the quaternary structure. This is how we see the protein itself. This comes from a primary structure, so it folds based on the interaction that it has within itself. So it has, let's say, hydrogen bonding, and then different let's say electrostatic interactions, and due to those intrinsic interaction, it converts itself into a tertiary structure as well as then into a quaternary structure. I can open my camera as well, right? Just right. Right. And so, right. And these proteins, so they are different. Functions of protein as well. Right? It can be used for regulation. So there are different regulation mechanisms inside our body that are responsible to act on the protein concentration as well. So some protein, let's say, keep the regulation on or keep the regulation off. There's structure, so the protein is responsible for, let's say, having the structure as we see it. So the eye itself is the body itself is made up of lots of different proteins as well, right? There's the immune system, so the antibodies are basically made up of proteins again. Then there's catalysis, so the body converts reactants into products based on the different enzymes that we have inside our body. Then there's signaling, right? So we have different signaling mechanisms that are also based on proteins. There are different proteins that stores, similar to what I have used. So the ferritin uh, protein that we have that stores iron inside your body and regulates the iron concentration inside our body. So proteins have different, let's say, functions. So the proteins that I have used are protein cages. So they, if you remember how the coronavirus looked like, so it was a circular spherical body similar to what we have. So it can be natural as well as artificial. So, and it could be viral origin as well as let's say mammalian cells as well. So protein cages are hollow compartments. It can be hollow because we can take out. So if it's a viral cage, those have RNA or DNA inside. So we can take that RNA or DNA outside and use this as a hollow cage, right? And then we can put our cargo inside. They are uniform size. So every cage that is found, they would have a certain amount of or a definite amount of protein monomers. So the result is that it would have the same size and shape. They can disassemble and assemble in based on the. So if we change the pH, this would open up, right? So if we do know that the cancer cells might have a different pH, right? It's slightly acidic. So what can happen is that if we design the if we can design the uh, if we can design the protein cage that it opens up at a lower acidic pH, what it does that when it goes to cancerous cells or the subcellular components that have a different pH, it would open up there. So we can direct these protein cages to open up only on that explicit pH, right? And it can be used for different guest molecules, so different cargo materials, right? And they are found in different shapes and size. So again, they are as small as 5 nanometer. They can be as big as 100 nanometer as well, right? So we can basically put lots of material inside and then deliver. So there are some viruses that are 100 nanometer, but there are also some naturally available protein cages that are very small. So based on a different structure and shape, we can use them differently, right? The idea was to make, let's say, high order structures. So these are protein subunits. If you can see, these are, let's say, some small subunits, and they basically self-assemble to form these kind of a structure, right? This is how the structure of protein cage looks like in terms of, and this protein cage structures can be used to high order, let's say, protein cages. And that's what I've done in my thesis as well, right? Right. So the example of high order structure. So this is one of the paper from David Baker's lab. Is that the David Baker is the person who basically won the Nobel Prize last year. I think he basically is responsible for making artificial enzymes or proteins. And you should look, if you're interested in that, in this particular subject, maybe you should follow David Baker's lab as well, because they basically publish every week. And what they did was is to make a high order structure based on the protein they found, or let's say created in their own lab. So using gold nanoparticles, which are charged, or they can form this kind of structures. Again, you can use this to make different structure and then change the orientation. So with oxidation, it changes to, let's say, a single, it changes this type of structure. But when you reduce these interaction, it can go back to its original monomeric state. You can use this to, let's say, have different structure inside and have different crystals as well. Slightly more advanced in terms of what you can do with structures. So, right. So just the summary, this would be the last slide that of the scientific work that I've done. So what I did was biomolecule-based structures, so OTE origami. So these are basically 6 helix bundles. So this one helix is double-stranded DNA, and you can fold. So like I said, that you can fold the DNA into different shape and structures. So I use 3 different type of let's say structures. This was, and then the Dion origami itself, right? So two different. So what I used was this compound called zinc phthalocyanins. This is basically, it's one of the, so if one of the treatment for cancer is photodynamic therapy, right? And what I did was use these two 6 helix bundle and this compound to form hybrid structure out of it, right? And this can be used for photodynamic therapy, right? The photodynamic therapy is that when you have this compound, right, this phthalocyanine compound here, what it can do when you put this certain light, right? In this case, it was a red light, where the drug is present. So if it's present on, let's say, this part of the body, when you put light on this, only this area would kill the cells, and not the entire cell. So this cannot work without the light, let's say the red, specific red light, so red wavelength light. You cannot, so that way you can only kill cells on that particular area. And that way you can basically have you can spare the healthy cells basically, and just kill the cells that are here, let's say. uh, and this was one of the projects. So the idea was to protect the DNAs as well as to inhibit the hydrophobic interaction of these molecules. So what the problem was that when we are putting this in water as it should be, this was aggregating, and then when it was aggregating, it was losing its functionality. And then by putting this on top of the DNA origami, it basically reduced its aggregation, because it was on top of this, right? So it's not aggregating, it's not coming together, and we can still use it, right? Similar thing was done with the similar, let's say, phthalocyanine, and I used this 24 helix bundle for the same cause for photodynamic therapy, right? With protein cages, I use this apoferritin or ferritin. So if it has iron inside, it's called ferritin. If it's empty inside, it's called apoferritin, right? So the ferritin, it's also inside your body as well. If when you go for lab studies, you probably have seen that they also test your ferritin levels, and that's the cage that is responsible for storing iron. So if you have less iron, this protein cage would be less inside your body. But the reason I used was to make crystals out of it. So what I did, if there are any pharmacy students, you know what a cyclodextrin does. So it's basically a host guest molecule. So the molecule, a single molecule that is hydrophobic, that can go inside, right? And this was charged on both sides, and this is negatively charged, this is positively charged. Once these are mixed together, we can form these crystals, right? And this was used for water remediation, for filtering water. So what it can does is this molecule, this pillarines, this can hold organic molecules. So in our part of the world, let's say South Asia, we have a really big problem of, let's say, having uh, organic molecules. So people put dyes, let's say those color dyes, right? Those are extremely organic molecules and can cause, let's say, problems when they are taken inside our body. So what it does, that it binds to, let's say, methyl orange. In this case, that's an orange compound that people use for uh, dyeing clothes, or let's say any other object. That can basically bind to this, and this ferritin, it has an intrinsic functionality to bind cadmium and cadmium ions or arsenic. These two compounds are again responsible for polluting the water, right? So this itself, the whole structure can be used for both organic as well as inorganic materials. So the arsenic and cadmium can go inside this molecule as well as the organic molecules, similar to what this molecule is, like in this case, methyl orange. This can simultaneously take both organic and inorganic molecule, right? The other protein that I used was green lantern protein. This is similar to green fluorescent protein. That's the most commonly used protein in biotech world, to have, let's say, fluorescence. And what I did was I made bio LEDs. So this was basically making a sustainable way of putting lights using only protein. So at the moment we use inorganic material to light up, let's say, our buildings and everything. So the idea was to use this for making bio LEDs. So just proteins can be used to make light, basically. So we used a different wavelength to brighten this up, and then that could be used as. So this was a proof of principle uh, uh, concept to use this as bio LEDs, right? Right. So that was finished, right? Time at Durham. This I started my postdoc in Durham in 2023. It's a very highly diverse interdisciplinary group. We have different people from different background. It's a really highly diverse group, like I said, and that's very useful in terms of doing cross-disciplinary or interdisciplinary research, where you have voices from different, let's say, subject matter experts. Right. It's a newly built lab, so I get to play with new toys, new machines, and everything. So it's built from the top. Uh, then it's a beautiful city again. It has really good cathedral. It's really green, and then it's quite peaceful in terms of, let's say, living life. Um, it's disruptive science. So what I am doing at the moment, which I think is that using artificial enzymes, or let's say making let's say different bio-nano machines. It's a disruptive science in terms of I'm not following any other paper or any old technique. I'm making new things out of different, let's say, things that have not been done before. So this is kind of disruptive science that I wanted to do, let's say, after my PhD. So that's really good. Working in academia, this is sort of giving a flavor of how to like working in academia. So it's a really flexible and autonomous work environment. I think what we do is we create our own projects, and we have, so I'm responsible for my own project to carry it forward. So I can take as many as project I want, and then I decide which project I would be working on each day, or for any week. So that's where it's very autonomous and flexible. Opportunities for research and collaboration. So I have great collaboration with different labs in the world. So people basically come from different lab to our lab. We basically go to different lab to work with them for, let's say, some periods, or let's say have different conferences to, let's say, go for, and then work with them or have collaboration with them. So it's really good to have networks and then do collaborations with. It's a vibrant, engaging community. So people are really ready to help you out, right? So if you have any difficulty, let's say in your experiments, there are people that would help you, or they have done similar experiments, so they would help you with your experiments. So it's a really good, like, engaging community as well. So there's intellectual freedom and stimulation. Again, you would think about your project while sleeping, while having a bath. So it's really, so you can think about your project as much as you can, have different experiments done. So if you, so the only person that would stop you from doing an experiment is you, basically. um, you would have intellectual freedom to test every different. So what I've heard is when doing research in industry, you have to stop at some point if it is not working. So because it becomes financially in let's say not suitable to continue one project if it's not working. In academia, you can work for, let's say, in a year and still say maybe it's not working, and you can still continue that because there's no stopping period, or you basically have funding. As long as you have funding, you can still work for those experiments or projects. Um, Things which I wish someone had told me before is that learn languages, explicitly programming languages. I would say learning these languages would help you a lot when, if I see the world right now, and then when AI is into everything, even the medical students or the pharmacy students, they, I think it would be better to at least have some basics of these programming language. I see Python softwares, and then what happens is that you get a software, but sometimes the software isn't as updated or as the way that it should work, right? And if you have some programming background, you can still work your way out and then do some, let's say, programming or some simulation to get what you want, right? And sometimes it's really easy, but then if you don't have the background, you would start from scratch, and it won't look great. But if you have the background, right, and even those languages, like apart from English and Urdu, I think it would be better to have, let's say, at least one language. I see many, let's say, people around me that they have at least 5, 6 languages under their belt. So it's really good to have at least one language, even languages that are not spoken in Europe or anywhere else, like I would say regional languages, even regional languages which I would say apart from Pakistani languages, right? So we do know Sindhi. I probably do know some Sindhi or even Gujarati, but I would say learn languages that are spoken mostly everywhere else. That would basically help you. I would recommend you to learn Blender explicitly. So the images that you see on cover pages, on scientific journals, or the images that I have shown you before as well, most of them were prepared in Blender. This is basically an open source 3D graphic designer software, and you can basically learn it by yourself using YouTube videos. It's extremely easy. Once you get hold of it, you can basically make lots of really great images and even animations. I would probably recommend you to learn this before it doesn't take time. Well, it would take time at the start, yes, but once you get hold of it, you can basically make really good images out of it, or even animations. Network with people you would aspire to be in future. So just have informational interview with people you think, I want to be, let's say I want the person, a researcher that you think has done similar research, or you would like to do some research, have an informational interviews, let's say on LinkedIn, have their 5 minutes to ask them, okay, how did you end up there? Let's say I don't want, let's say, a recommendation letter. I just want to know about your journey. Like, how did you end up there? What would you do differently if you're given time? So just have, let's say, a good network with people you want to be, let's say, in the future, right? And one thing I basically would like to emphasize as well is that if you want to follow research, have an interdisciplinary science approach. So mix everything: chemistry, physics, biology, material science together. What I was struggling before is that I didn't had great, let's say, background of physics or material science. But now when I started, I had to, let's say, learn a lot, or had a really steep learning curve in terms of learning material science or physics. So I would rather suggest that if you want to, let's say, if you want to do research, because I see the world have like doing interdisciplinary science, so we don't now limit ourselves to just biology or pharmacy. We are integrating even maths, let's say, or biology or chemistry or physics all together to find a solution for one problem. And that's where I see the world going forward. So I would recommend you to, let's say, have an interdisciplinary science approach. So learn, let's say, different interdisciplinary courses from online platforms. Have webinars from different, let's say, different scientific fields, and that would probably give you a perspective that how people think differently in different field, or what I can get, or let's say, can I have an answer of a biology problem from a material science seminar. So think differently, and that way I think it would give you a better perspective to move forward explicitly for interdisciplinary research. Right, and I think that would be it. Uh, yeah, thank you for listening, and thank you for inviting me as well. Right, questions.
Okay,
Thank you.
that was so well explained. Everything was really good. So I want to now go towards the questions. So if you have any questions, the floor is open. Please drop down your questions, and I'm going to start with a few. So we have like, are protein cages currently being used in practical applications, or are they still primarily in the research phase?
Protein cages. I think if you look at the vaccine that we have, the vaccines that they use is adenoviruses. So this is basically being, so if so this is a different perspective, right? They are being used, right? So the vaccine that I think Oxford created was an adeno based subunit. So I think they are still being used. It's not far away from, let's say, using those protein cages itself. So I would say they are in the pipeline as well as being used.
Okay, so We have another question by Bilal Urshid. He's asking, what are the challenges you face in developing nanoparticle drug delivery system?
Uh, the 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 challenges of making drug delivery systems. So it's different for every drug delivery system. So for DNA based, right? DNA origami, right? So what happens is that if you are putting DNA origami into your body, right? The body itself would have protection mechanism, right? So it would act against it. So body has enzymes that would break down uh, those drug delivery systems, right? For that, I had to create a let's say this a protection layer of the compound that I had, and that basically protected it from let's say getting digested, right? So every different platform has its own problems with the lipid particles that people are using currently. So doxorubicin is basically used with lipid particles. The mRNA based vaccine that we had from Moderna as well as Pfizer was basically using a drug delivery system or lipid nanoparticles as well. So the problem is that we don't know how much cargo is there. So different platform has different problems. So if you're working on one platform, you probably would know the problems of that particular platform, and you have to work around that.
Okay, that was so well explained. We have another question about, do you think bio-nanotech has a strong scope on industrial side?
I like I said that people are using this approach well now. So if I remember, most of the drugs that are, let's say, rejected in clinical trial is because of the solubility of a problem, right? So they are not soluble enough to get a response. So and that's where the drug delivery system or bionanotech comes in, right? So that can make the drug soluble enough, or that can make the drug, let's say, protected enough to, let's say, stay inside our body. So I think it is being used. If you look at mRNA based vaccines, again, that is bionanotech, and that was used really fast in terms of how it the research went through. It was like available in 2 years to everyone, like 1.5 year to everyone. So I think it's going very fast at the moment.
Okay, also I have a personal question. How did you decide that you wanted to do research instead of industrial, towards the industrial side, go towards the industrial side?
Industrial side in terms of corporate job or research, like in industrial research.
Like corporate job.
Right. So the so when I shifted from AKU to Sanofi, I think the idea was to have time to prepare myself to go abroad. Right. That was something I did just to, let's say, have let's say the financial wheel going. Right. The only reason that I joined Sanofi was that. But I think I can take away a few things while I was working in Sanofi, right? Uh, I don't regret working for that, but I think I was pretty clear while I was doing my pharmacy that I want to pursue research, explicitly doing vet research. Yeah, that was the only reason that I did it's in a corporate job. But apart from that, no other particular reason. Yeah.
Okay, we have another question from Sayyida Qaula Hussain. She's asking, can you suggest any journals or research articles that are essential reading for someone entering bio nanotech?
Right. Journals would be, so if you want a really like a thorough uh, overview of the field, I think there are two journals that I has really thorough reviews. So there's one chemical reviews, and then there's chemical society reviews. So I don't remember what's the publisher. So one is from ACS, the other is from RCS. So they basically give you a really thorough background, as well as so those two journals I think should be good enough. They are really big reviews, but I think that will give you in and out of every field, let's say. or let's say Bionanotech at least, or but they would probably have they they basically target chemistry as well as physics and biology. So I think you would get most out of it, but you probably have to let's say have some background. So probably you would have to search few words here and there to get most out of it, right? Yeah.
Okay, so that brings us towards the end of today's session. On behalf of IEEE Ziauddin University and BASME BME, we just want to give you a token of appreciation.
Thank
Yeah.
you.
So thank you, Mr. Ahmed Shaukat, for joining us and sharing such an inspiring and insightful story. Your journey truly encouraged us to explore new directions and keep learning beyond boundaries. So it was all of our pleasure to see your whole journey, like how you were saying that you started with those bus and now the way you are. It's amazing. Thank you.
Thank you.
Okay, and of course, thank you, our amazing audience, for being here and asking brilliant questions and continue to learn, grow, and dream bigger. Until next time, stay curious, keep building brilliant and adding brilliant questions. Thank you. Allah Hafiz.
Allah Hafiz.